presentation. Thanks a lot for the invitation. I always wanted to come to Geoquant, and it's a pleasure to be there, even if just virtually. I hope I can travel, we can meet soon in person. And yeah, this is Barcelona. Well, this is Sant Cugat outside Barcelona, so not even Paris. It's been a long time I'm not in Paris, and unfortunately I cannot go there yet. So, okay, my mini course is probably the most basic from what I saw of the mini courses. And let me explain that I have a very strong support from Pau Mir. This is a joint mini course where I will be doing some theoretical classes. Today is going to be extremely basic. And then Pau this afternoon, so in 30 minutes after my talk, he's going to do the problem session. Pau there, you can see him on the screen, I hope. Hi, Pau. So Pau is going to be responsible of these classes, and these problem sessions are very important because we have totally coordinated the theoretical part with the problem sessions. So it's good that you go to the problem sessions if you want to follow the next session, the next theoretical session. So what I'm saying is, please don't skip the problem sessions, okay? Let me show that we have prepared some notes. These notes are going to be, have to be improved. This is like a first draft of the notes, but you can find them on the website that I'm going to try to share now for you, on the website of the conference. Okay, if you go to the program, you'll find these notes. Okay, these are notes for the mini course. We have two versions of the notes, one with the solution of the problem sessions, and the one that is now available doesn't have the solution to the problem sessions. Okay, but this version with the solutions already exists, but we are hiding it from you. But at the end of the course, you have also the complete version with the solution. So today, in my first session, today is going to be about very basic stuff. I'm really assuming that you don't know symplectic geometry. Okay, so the ones who know symplectic geometry can really skip this class. But the purpose of the class is to understand the basics in symplectic geometry and quickly focus on integrable systems. What is the connection of integrable systems with quantization? Integrable systems provide a source of what we call polarizations in geometric quantization. So this is our point of view of this mini course, is to compute geometric quantization using integrable systems. Okay, and these integrable systems in particular include toric manifolds. So there is a lot of connection between my course and the course of Kota in the mornings that starts tomorrow. And I encourage you to follow both courses in a way in parallel. Okay, so well, today everything is going to be basic, but tomorrow we are going to go really to the quantization business. And the idea is, but the class of today is important because our point of view of quantization is going to be initially following the point of view of Constant, okay, and following it full force, independently of the fact that maybe our polarization may have singularities. What does this mean? I will explain this, and this is what I will explain today. And then our approach, the approach of Constant to quantization, is to when you have what we call, and this will be explained tomorrow, global sections of the pre-quantum bundle, things are right because these global sections give you a good way to approach the problem. But when you don't have them, you have to do the computations locally or semi-locally in a neighborhood of maybe of a fiber, if you are in the toric case, of a fiber of your moment map, or more generally, if you are considering integrable systems, in a neighborhood of a fiber of your integrable system. And so the connection, the close connection between the class of today and the class of tomorrow is that because our approach to quantization is going to be using sheaves. Okay, somebody was asking about sheaves in the previous talk. This was who was it? This former student of Rui. And now, so will you have shifts? Yes, you will have shifts, okay? And shifts will start tomorrow. So as you know, the approach to shifts is compute globally, no information locally. That's more or less the motto of computation by shifts. And therefore, we need to have these local models, okay? It turns out that the local or semi-local models that we are going to have, this is what I'm going to explain today, are connected to, indeed, are very much connected to the cotangent lift. So this afternoon, the cotangent lift, I'm going to assume that everybody knows, but maybe people are not so familiar. And the ones that are not familiar with cotangent lifts, you have to go to the class this afternoon, okay? And Pau maybe will be brave and take somebody to the, I mean, maybe Pau will call you to the whiteboard. I don't know, Pau, what do you think? Maybe we have some volunteers even for the cotangent lift.
Yes, I may ask some questions to the general public, but I think that the screen sharing for participants is disabled. I don't know if
okay, so if somebody
taking someone to the blackboard, but I can ask questions to.
You can ask questions, right? Maybe this is something that we can ask Mara to give full. If somebody wants to do a problem on their iPad, is there a way to solve this?
Yeah, that should be possible.
You can give Mara, you can give this person full force. For instance, like Pablo Nicolas is around. Maybe Pablo wants to go on the screen this afternoon. Okay, so more or less, this is to tell you how our course will work. There are going to be 3 sessions which are going to be theoretical and 2 sessions which are going to be problem sessions, but they are interlaced. So it's very important to attend the problem session. So also there is, I mean, here there is some material that it's not perfect. Okay, these are some notes. These notes can be improved, will be improved. And you know, well, life is always a process of perfection. So if you have comments to the notes, we will be glad. And you see typos, corrections, we will be glad to have your feedback. These notes can be found here on the website here of the conference, here, lecture notes. And I'm also going to share with you the notes of my notes, okay? My slides today. Let me do this. How can I do this? I'm going to stop sharing because I don't see anything. And let me go. Maybe Pau, do you have here the link that I sent you? Yeah, I have it here. Okay, I have the link. And then, I don't know, I'm going to put it in the chat. Wait, I'm very slow. Okay. These are, I mean, you are getting here a link to my Dropbox, direct link to the slides that I'm going to be using. So, well, my plan is to be using the slides and also to be using my iPad. Let's see how effective I am doing all these things at the same time. Let's check. Okay, so let me start sharing the slides. As I said, today this is going to be very basic. And okay, well, these are the slides that you see here. Let me put the slides directly, stop sharing. Framework 1 here, share. Okay. Okay, so there we go. That's the mini course. So today I will talk about introduction to symplectic geometry. Everything is going to be basic and integrable systems with the hope of giving these models, okay, to with hope of giving you these models to compute shift quantization tomorrow. Okay, this is more or less the beginning of any talk in quantization. Okay, today we got Stefan with his approach to quantization, and my approach to quantization is going to be that of geometric quantization. Okay, so essentially geometric quantization wants to establish this translation, this kind of dictionary between classical and quantum systems. And for us, the observables are going to be the functions, and we want to, in a way, associate operators to a Hilbert space. So indeed, what we're going to do in this mini course is going to be just this first step. It's going to be construction of this Hilbert space, which we also call representation space of this classical system. We are not going to be able to go a little further. Okay, so in this mini course, I will give you a model to construct representations. Okay, and I will discuss, and these representations will depend on extra data, and this extra data is going to be an integrable system. And let's say a big point in geometric quantization, a big question, an important issue, is that of dependence on your data. Okay, so you can discuss, does your representation depend on your initial data? Okay, and that's a difficult question. Okay, and indeed it turns out that already tomorrow we will see examples where we see that our approach with polarizations depends much on the polarization. But the last day we're going to be happy because we'll see what happens in the toric case. We will also analyze famous cases when we take an integrable system. There is a whole school in integrable system working on the semi-toric case, which are systems that have some singularities called a focus time. So I will also consider those, and I will also quantize those systems. And then I'll compare to the toric case, and I'll compare to Keller quantization, which is going to be the viewpoint that we will see in the course of Hattori. So there is a lot of intersection. Okay, so this is indeed our love story, that we want to associate a quantum system to a classical system. And well, the cartoons I mean, the cartoons, I feel very much identified with these cartoons, because look, here is the mathematician working like crazy, right? You can give your own definitions, your actions go on, and you spend all your life, but what have you been doing, right? And well, the truth comes here with this other comic, that maybe you have been all your life working quantization, but then when you get to heaven, if there is such a thing, and if you go to heaven, maybe you don't go to heaven, okay, then St. Peter is going to ask you about your sins, and you have to declare. And the truth is that we still don't understand quantum theory. That's a little bit the message of the course. So the message of the course is that this gives you a way, an approach to quantum theory. I'm going to discuss this approach. Our approach follows Costan approach, and I will criticize this approach. I will criticize it, especially when we have singularities. But I will also correct. When we have singularities, we'll see that if we have a compact system, what you expect is to have a representation of space which is finite dimensional. It turns out that if you take Costan, the definition of Costan, and you allow to have singular orbits of your polarization, it turns out that this explodes, and you may have infinite dimensional contribution. But precisely with Paumir, we found a way to correct this. So this will be the end of my talk, of my mini course. And indeed, when it comes to singularities, also we can think that the singularities maybe are on the integrable system, and there might be also on the symplectic structure. And that's something I will maybe present today, the definitions of what I mean by singular symplectic structure, and we'll get to it just the last day. So that's what we call geometric quantization in a nutshell. What we need to know is that the starting point is to have a symplectic manifold whose symplectic form defines an integral class. Okay, do we have the right to think that this form, which is symplectic, defines a class, a cohomology class? Well, this is true because it's a closed form, but I'm going to give the definition of symplectic form because it's the first thing. So what is in gray, this will not show up today. I mean, what is in gray will be discussed tomorrow. There is a complex line bundle, indeed, Hermitian complex line bundle. There is a connection related to this symplectic form. And there is something which is flat sections that I have mentioned here in the introduction, in the preliminaries. But this is something that these things in gray will show up tomorrow. Today, I'm going to ignore completely connections, complex line bundles, and flat sections. Okay. So today I want to concentrate on if these are the ingredients of geometric quantization, I want to concentrate on the first ingredient, which is a symplectic manifold with an integral class. Well, I will discuss tomorrow the integrability condition, and I will discuss what is a real polarization, because the polarization can be complex, okay? I can look at polarization in a more general case, and then I can compare this real polarization indeed as a limit. This is what Kota will do in his course, I think. But I will not do this, so I will assume from time zero that I take a real polarization. This means that I take a Lagrangian foliation of my manifolds. And what is the connection to integrable systems? That integrable systems provide natural examples of these real polarizations. Okay. So why symplectic geometry? Okay, why do we care about symplectic geometry? If I'm going to assume that you are one of these students who know nothing about symplectic geometry, then you are in the right place. Okay, you can start from zero here. What do you know? Well, probably you know about classifications of surfaces, right? Topological classification of surfaces is somebody everybody knows, and I can assume this. And everybody knows that if you consider a Riemannian structure on your manifold, then you get new invariants, because we know that curvature is an important invariant. Okay, curvature indeed is a local invariant already for Riemannian geometry. And this is the kind of things that we learn already in our undergraduate studies, because this is like the classical way to look at nature is by measuring with a Riemannian structure. That's the natural way to do it, and this is what we study in the undergraduate study. But what if I take your metric and I break it and I give you an area form instead of measuring things? Let's measure things with area forms. Okay, what is an area form? Well, I can think that it's an antisymmetric object on my manifold, on my surface. Okay, so instead of taking a metric, I take an antisymmetric tensor. Okay, and this is an area form. And well, can I do this on a non-orientable surface? Oh, no, I cannot do this, because as soon as I have an area form, I know that the surface has to be oriented. So let's throw away all these non-orientable objects. Okay, so let's take, on the two-dimensional case, let's take a closed two form that doesn't vanish. Okay, and in the two-dimensional case, that's a perfect definition for what is a symplectic structure. And there is a theorem by Moser which classifies these area forms on a surface. And it says that if you have two area forms which describe the same symplectic class, okay, and this is because, well, here you are two-dimensional, so of course they are going to be closed, these two forms, because you cannot have three forms. Okay, so they are going to define cohomology classes. Okay, and then Moser completely not only understood these objects, but completely classified. Indeed, Moser, this is in a paper in which he was trying to understand volume forms, the problem of classification of volume forms on a manifold. But if you take a volume form in the two-dimensional case, this is an area form. Okay, so Moser classifies area forms on a surface or volume forms on a manifold just using the cohomology. So this is telling you that already topology is telling you what is the classification. And the idea behind is a powerful method that I'm going to unshare now. Okay, let's see how bad I do this. And I'm going to try to share with my iPhone. Share. Okay, now it's when I enter. Let's see. Okay, here we are. Okay, you can see this. Can you see the screen or not?
Yes.
Okay, thank you. So let me close this. Okay, I go to notes. Okay, and let me take this note here. Okay, here I am. I want to discuss, this is Moser equation. So the situation is the following. I have two forms, two area forms. I'm going to say omega 1 and omega 0, which define the same class. As they define the same class, I know that this is equivalent to saying that their difference is the differential of beta. Okay, this is what I have written here. That's the condition of Moser. Then Moser, he was very wise because he takes this beta. This beta is a one form. Here I just use the definition. Here, the only thing I did, let me see if I want to change color. The only thing, let me pick up this color, okay? This beta here, okay, just comes from the definition, okay? I have two forms, two forms that define the same cohomology class. Okay, then the equation I look is the following equation. I look at this equation. I do the contraction. Beta is a data. What is omega t? Omega t is the linear path of forms that connect omega 0 to omega 1. Okay, so I want to be in time 0, I want to be in omega 0. And in time 1, I want to be in omega 1. So that's the path I consider. I consider a linear path. And then I look at this equation here. Okay. Well, then there are issues here. Can I assume, okay, here we are two-dimensional, and the thing is that it's very simple to check that this is 0. And then you need to check that these guys here define a path of non-degenerate forms, okay? But because these are area forms, it's easy to check this, okay? Then what Moser did is to look at this equation here, okay? And then, so the equation of Moser is this one. So now here you have the data, this is data, and this is unknown. So this is your unknown object. Okay, let's change color. This is your unknown object here. And then what you do is to take the path, you look at these solutions. Okay, I should do phi s for s equal t. So I take, this is a t. So I take the time one, so this is a time-dependent vector field, and I take its time-dependent flow, okay? Now, okay, now we need to recall some formula that you can find in the notes, the proof, and that's important. Look at notes. Because the path method, I'm explaining the path method because the path method is the key to everything, almost everything in symplectic geometry. Well, that's false, okay? But let's say if we want to construct a symplectomorphism, that's the best way to do it. And still nowadays it's used in current symplectic topology. So the equation that I'm gonna use is this equation that if I have this differential, I have such a condition. I'm going to use this. And then what happens is that, the following, that I can compute the differential of omega t with respect to t. I have my omega t here. This is the linear path. So I just do the differential of the omega t, okay? And what I get is that this is just the differential of the path that I was considering. And this is just omega 1 minus omega 0. And now I look at the second part. I look at the Lie derivative, xt omega t. Okay. Now I look at the Lie derivative of omega t, and I recall something that is fundamental and that I'm also going to assume that everybody should know by now, which is Cartan's magic formula, which tells me that you have this connection between the Lie derivative and the contraction. So if I apply this formula here to the Lie derivative, what I get is the differential of the contraction of x sub t d omega t plus the differential, okay, of the contraction. Now apply this to xt of differential omega t. Okay, so I should have done this in a different color. Let's choose. This is Cartan's magic formula. Okay, and then what happens is that, change again, when I plug this here, of course this goes to 0 because
sorry, is there an extra d in front of omega in the
where in front of omega
in Cartan's magic formula?
Ah, yeah, sorry.
Yeah.
Sorry. Yeah, that's why, I mean, you know, very wisely, this guy was showing me the eraser. I say why this iPad is. Thank you very much. That's the nice thing of the iPads. These error never existed. Indeed, there was this, there was the thank you. Okay, so that's, I just, and of course I have to erase it here. Thanks a lot. So now the only thing I do, I don't know why I put here this. Well, what I get here, let me go back to writing. What I get here is just differential of contraction of x sub t omega t. Okay, therefore, why I'm doing this? I'm trying to solve the equation, okay, which I will write again. I will write it here. I will put it in red. That's the equation I'm looking at, minus beta. Okay, that's the equation, that's Moser's equation. Okay, and that's the equation I'm looking at. And okay, what do we get here? I get that this is exactly minus, if I plug it here, because of this equation, this is minus differential of theta. Okay, but this has, what I have done is just to compute the Lie derivative with respect to x sub t of omega t. And now I'm doing something that you hate, which is go back to this formula here. And look, this is omega 1 minus omega 0, which is plus differential of beta. So the sum of the two things, when I consider this differential, when I do the differential with respect to t, gives me 0. So this implies that the differential with respect to t, the differential of what I'm doing now, so I have phi t star omega t with respect to t, that this thing is 0. This means that this guy here is constant. And what about taking the definition when t equals 0? Because phi t is a flow, this has to be the identity. And therefore, this is telling me that the flow takes everything to omega 0. So what I have done now is to prove that if you take, Tim Henk has a question, go ahead.
Sorry, I had a quick question about Moses' equation as you wrote it down. Because on the left-hand side, is that the iota or the?
It's a iota. This is a iota. This is
okay.
A very bad iota for
Okay,
somebody who is writing.
Excellent. Thank you.
That's a iota. So I do the contraction, okay, of the two form with the vector field. So I define the vector field in this way. Why this vector field is uniquely determined? Because omega t is non-degenerate. So omega t gives me an isomorphism between the cotangent bundle and the tangent bundle. This works, I'm doing this in dimension 2, and this works in higher dimension. I will recall this. So what I'm doing now for surfaces indeed works in general. And I think the path method is great. This is what I'm explaining in this proof. Okay. For the proof of the Darboux theorem that will come later, I will do the everything boils down to the same thing. That's why I chose this. Okay, once we are, what I have done here is to prove that if you take the flow, the time t flow of this vector field, this time the flow, it's going to take, it's going to deform your area form, omega t to omega 0. And this works well in surfaces, because in surfaces it's automatic that the path is going to be a path of area forms. Okay, this is not automatic in higher dimensions. Then you need to assume this as a condition if you want to have a similar statement. There is an issue though that I'm skipping, but it's very clear. Why is this vector field integrable? Okay, the manifold is compact, okay, and therefore things are simple. Because the manifold is compact, I can integrate on all the manifold and I have a flow. So this flow is well defined. Okay, so I use this flow to integrate, and this flow, what it does for you is to deform your symplectic structure to the initial symplectic structure. This method, which is called Moser's path method, it comes from this paper about equivalence of volume forms on a manifold. It's very powerful because you can now put additional data. For instance, you can have a group acting there. Then you can make this trick equivariant. You can do many things with this trick. It's fantastic. Okay, I'm going to stop now sharing this. So what I have proved for you is the classification. I have proved this classification theorem. Okay. Any questions so far? I'm quite bad at following the chat, but I'll try to look at the chat. Okay, let's go on. Okay, so here, this is exactly in this proof we have seen that what happens in general, if I take what is going to be a symplectic structure in general, is going to be a non-degenerate close to form, which in dimension 2 is just an area form. And this non-degeneracy that I have used in this proof already, because I have said that there is a unique vector field X sub t satisfying what we call Moser's equation. Okay, this non-degeneracy gives me a natural isomorphism between the cotangent and the tangent. Okay, the idea of this non-degeneracy that was already present in the proof that I just did of Moser's classification theorem. Indeed, the inspiration comes from Hamiltonian, from the definition of Hamiltonian vector field. In the proof, I was using a one form. Now, if I take exact one form, it means that I have the differential of a function. Okay, then I need to solve this equation. Here, the iota is more clear. I hope that Tim can now here in LaTeX, there is no problem. And here, the equation that you look is that you take the differential. Where I tend to put a minus sign. We can discuss about it later why a minus sign. And then the solutions of these equations, okay, then the vector field that you get here, you take a form. Now I don't assume that it's t dependent, okay. Then the solutions of this equation are exactly, these are, this is the Hamilton equation. This is the Hamiltonian vector field associated to this function. And this function, usually the meaning that you have is that usually you have the energy of your system. So most of the examples that you find have a physical interpretation, as you will see this afternoon, okay. Now, an interesting fact is that if you use as omega form what we call the Darboux form, okay, where the Darboux form is just the standard form. Well, I will see it in next slide. Sorry, well, now I don't want to jump again to write in my iPad, but this is just the differential of xi wedge di, okay, the differential of dxi wedge dyi. So you take just a constant form, which is the simplest of the forms, and then you solve this differential, this equation here, and you compute the flow. If you compute the flow, well, instead of coordinates xi and yi, you take coordinates pi and qi that we put in a compact way this way, but you can think that this q can be qi. Okay, then these equations are just the equations of the flow of the Hamiltonian vector field associated to the function h, okay? And these equations are indeed what we call Hamilton's equations. So Hamilton's equations can be interpreted exactly in this geometry, okay? So this is what I have just said now. And well, symplectic geometry, you can think of it as a geometry governed by a form, which is a two form, which is non-degenerate and closed, okay? And then the main objects and the main motivation and the main for the theory is the study of Hamiltonian vector fields, which are given by this equation. And there is, of course, an analog of this in the contact set for odd dimensional manifolds, which are contact structures. Contact structures are governed by a one form instead, okay? And then, you have instead of the condition that is closed, you have a non-integrability condition. And then you have the definition of Hamiltonian vector fields, but the most important or the first object that you are interested in is that of red dynamics, where the red vector field is associated to the form in this way, okay? So contact geometry is a whole different business, and it's related to quantization because we could think sometimes of the prequantum, the total space of the prequantum bundle with a contact structure, but I will not enter to this. So what we need to know about symplectic manifolds is that locally, and that's a big difference with Riemannian geometry, locally any symplectic form can be written in Darboux coordinates. I already said it, any orientable surface is a symplectic manifold, okay? Then examples other than orientable surfaces. Well, you can do products here to go to any dimension. That's a way to go. You have cotangent bundles, okay? You can wonder which spheres can be symplectic, can have a symplectic structure. And this story is very quick to solve because if you have a compact symplectic manifold, then your symplectic structure, okay, cannot be exact. Therefore, the symplectic structure defines a non-vanishing cohomology class in the second cohomology group. Therefore, you cannot find a symplectic structure on, for instance, on S4, okay? And you have the proof of this fact in the notes, okay? So as example, if I look at the spheres, would be the case of a two-sphere, okay? Because it's the case of a two-sphere, clearly it's an orientable surface, therefore it's a symplectic manifold. And then I have, well, a very classical example, and the one that motivates the whole theory is that of cotangent bundles, in which the symplectic structure now, because cotangent bundles is non-compact, I have no obstruction to being exact, and indeed the form is exact, and the form is minus the differential of what we call the Liouville one form. And the Liouville one form is going to be a main character of the class after my class, the class by Pau, because it's fundamental to define the cotangent leaf, well, to define the moment map associated to a cotangent. Because there is a magic thing going on with the cotangent bundle, which is that you can lift objects to the cotangent bundle, and then if you have a group action that is anything on your manifold M on the base, okay, then the lift of this action to the cotangent bundle is going to be Hamiltonian. So this is amazing. So you get for free examples and examples of Hamiltonian actions just using the cotangent. Okay. I mean, more this afternoon about this. As I said, in dimension, we classified two-dimensional symplectic manifolds, and this is very good. And we cannot go to higher dimensions. This is a complicated story. And again, Mosher's path method that I showed you before is still the most famous trick in symplectic topology nowadays to the form. In higher dimensions, can you classify symplectic manifolds? Well, sometimes you can classify very easily if you have additional data. Now I'm going to define what is a toric manifold. Okay, a toric manifold for a differential geometry. Of course, for algebraic geometry, you have a different definition, and surprise, they are equivalent. Okay, what I have, what is a toric manifold? A toric manifold is just, I consider a symplectic manifold, and I consider a group action. Okay, and I assume that this group action is Hamiltonian. What does this mean? Well, I have it, sorry, I'm going to go a bit farther. I skipped this. Okay. Hamiltonian action I can define it in the following way. I have a group action, and I say the action is Hamiltonian. Essentially, the idea that I need to have is that the fundamental vector field, okay, associated, given a Lie algebra, an element of the Lie algebra, I can always associate a fundamental vector field on the manifold. So I need to assume that all the fundamental vector fields on the manifold, okay, are Hamiltonian. That's the first condition. But there is a second condition. There is a kind of collective condition, which is, this is why I need to impose that there exists a mapping from the manifold to the dual of the Lie algebra, okay, such that when I look at what is called the X component, the mapping from M to the Lie algebra, okay, this is the dual of a Lie algebra, therefore I can pair with an element of the algebra, which is X, and this is the pairing. Then the only thing I say is that this pairing here, which you need to think about it, okay, mu is a map from M to the dual of the Lie algebra. When I do the pairing, I go to R, okay? So I have a standard function on my manifold. So what we need is that this function, okay, is a Hamiltonian function. So what I need is that if I take this function, the Hamiltonian vector field coincides with the fundamental vector field with respect to the element of the Lie algebra. First time you see the definition, you don't understand anything. That's normal. You need to go over this definition again and again. And there is a second condition, a little bit, to put a little bit of order, which is equivariance, that in the case in which that I'm going to omit a little bit on insisting on this, equivariance with respect to the group action, and here the coadjoint action that you have on the dual of the Lie algebra. But I'm not going to insist in equivariance, because in the case in which the algebra that I consider is abelian, which is the only case I will work in this course, then this condition of equivariance is equivalent to assuming that the moment map, that this mapping here containing this basis of the Lie algebra and containing these elements of the Lie algebra, these components, that this mapping is equivalent, is invariant with respect to the group action. Okay, that's the only thing I need to impose. That definition is a bit, may look, first time you look at it, a bit strange, okay, but it's the natural definition behind the examples of moment maps. Well, indeed, this afternoon, Pau will do some examples that are non-abelian, okay, but in the course, we will consider just the abelian case. So now what is a toric symplectic manifold? I take a symplectic structure and I take a group action, which if the manifold has dimension 2n, I take a torus of dimension n. I assume this action is effective. Effective means that every element of the group at least moves one element on the manifold. The condition of effectiveness is not so important, because by quotienting you can always get it, okay? But I need to assume that I have a Hamiltonian action of a torus, have the dimension, effective, and then this is exactly what is a toric manifold. And then toric, what's great, and I'm going to go here, what's great is that toric manifolds are just classified by the image of the moment. Because, well, first, if you have a moment map of a group that is abelian, the image goes to Rn. Okay, so I have a mapping from my manifold of dimension 2n to Rn. Okay, if I'm for instance, if I'm in dimension 4, okay, then the image is going to be something in the plane. A theorem that it has opened a whole big line of research is that of Delsan, which tells the image of a toric manifold is exactly a certain type of polytopes that are called Delsan polytopes. So you can see things on your manifold. There is a one-to-one correspondence between toric manifolds and these polytopes. These polytopes have certain conditions, which are quite rigid, on the slope on their sides. Okay, and this is what we call Delsan. So there are certain conditions. But for instance, if a symplectic geometer sees a triangle on the plane, indeed the symplectic geometers automatically see CP2 with this torus action, because you have a kind of dictionary. And here there is a picture of Dusa McDuff. Why? because Dusa-Magdaf gave a counterexample in the proof that I have done of equivalence of symplectic structures on two-dimensional surfaces. This proof doesn't work in dimension 4. Okay, and there is a deep reason for this case, which is related to how does the symplectomorphism group of the manifold looks like this in infinite dimensional. And she gave a counterexample. Okay, and I also think it's nice to have always pictures of women who do research in mathematics, because sometimes you don't see them, right? So that's why instead of a picture of Elsan, I put here a picture of Dusa-Magdaf. Okay. Special submanifolds. So by the way, toric manifolds are important to me because they give particular example of integrable systems. So if I consider definition of integrable system will come later, but it's more general than toric manifolds. Toric manifolds, I can look at this moment map as a mapping from my manifold to Rn. And if I look at the components, because of the definition that I just gave of moment map and these invariants, what happens is that these components need to commute in the sense that they're Poisson commute, in the sense that omega applied to the Hamiltonian vector fields is 0. Okay, I can apply omega to 2 Hamiltonian vector fields, and this is 0. And this condition is a condition which tells me that toric manifolds define an integrable system. Okay, and this is why they are interesting for us. And they are, although they are a special type of integrable systems. Okay. Another important thing of toric manifolds, if I look at the fiber of the moment map, okay, the fiber of this moment map, it's going to be a Lagrangian submanifold. Okay. Why? Because I have this condition. Okay, let me I would like to explain this. I have 15 minutes, so I will not use my tablet now. Let's say the condition that it's Lagrangian, definition of a Lagrangian submanifold. A submanifold is Lagrangian if the pullback of the symplectic form is 0. Okay, so if I have this condition that omega applied to the Hamiltonian vector fields of the components of the moment map is 0, okay, this is equivalent to saying that the fibers of these toric manifolds are Lagrangian submanifolds. And Lagrangian submanifolds are important. I can also look at Lagrangian submanifolds from a more basic perspective, saying that the tangent space, this is the symplectic orthogonal that I can define as I do in Riemannian geometry but now taking this antisymmetric tensor. Okay, then this condition tells me that the symplectic orthogonal equals exactly the orthogonal. And indeed, if I have the condition that the tangent space is included in the orthogonal, this condition is an isotropic submanifold. And when is an isotropic submanifold Lagrangian? When the definition is when the dimension of the manifold is n. So Lagrangian submanifolds all have dimension n, half of the dimension of your symplectic manifold. Examples: on a surface, any curve is automatically a Lagrangian submanifold. As I said, a fiber of the moment map of a toric manifold. Interesting, the 0 section of the cotangent manifold. That's very interesting, because this is the model that we are going to have for any integrable system in a neighborhood of a Liouville torus. And the fibers of an integrable system. These are examples. Then I have these other coisotropic and isotropic important special manifolds that now we are not, today they are not so important, with one exception. When I consider an integrable system, definition next slide, then if I have a singularity, I may consider the orbits of the Hamiltonian vector fields. And then what I get is an isotropic orbit, because the orbit will have lower space. Okay. So here is the definition. Another woman in mathematics, Kovalevskaya, okay, known for the Kovalevskaya spinning top, okay, the study of the spinning top. And here, I mean, this picture here comes from KAM, and this picture here reminds us that we worry about Hamiltonian systems because we want really to solve problems of finding the actual trajectories of objects, okay? And this Hamiltonian is usually the energy of your system. This picture here is a picture of what is called the KAM tori that survive after perturbation, okay? And in order to understand KAM, or well, people working KAM won't agree with me on that, but I think for geometers, a good way to understand KAM is to say, okay, I have an integrable system, okay? If I have this kind of object, I have a special kind of normal form, and now I'm going to perturb this normal form, and I'm going to see if I still get some kind of invariance. And in order to talk about this picture, I need to introduce the definition of integrable system. The definition of integrable system is a set of functions. I copy more or less the definition of moment map in the toric case, but the difference is that I don't require that these functions, okay, satisfy this condition of collective first Hamiltonian of the system, okay? So I have functions on my manifold, and the only condition that I assume is that they Poisson commute. Here I'm using the Poisson bracket, and I wanted to write, I'm sorry, what is this Poisson bracket? This is just omega applied to the Hamiltonian vector field of Fi and Fj. Let me do this quickly with, I mean, time is passing by, but well, that's life, right? Let me see if my iPad is idle. Wake up. Okay, screen mirror. Okay. Let's go. Want to write a formula. Sorry, because I started very slow and then it's always the same. You think you don't have enough material and then you are talking and talking like crazy. So what I'm saying is, let me change color. Pink is a good color for this. What I'm saying is that the definition of bracket, Poisson bracket is a long story. There is a whole theory on Poisson brackets, which is called Poisson geometry, okay? I'll try to get to this on my last lecture, but today the Poisson brackets are associated to the symplectic form, and I apply them to the Hamiltonian vector fields. That's our definition of Poisson bracket, okay? Is this the standard Poisson bracket that Poisson defined? Yes. Is this the standard Poisson bracket when you consider the Darboux symplectic form? And it's interesting to do this computation. It's not in the list of problems, but it could be in the list of problems. Okay, and recall that what I have said is the definition of Hamiltonian vector field. This is the contraction of Fi with respect to omega is minus the differential of Fi. I have this condition. There is something very interesting about the Hamiltonian, the Poisson bracket, is that I can also write it as a derivation. It's a biderivation indeed. And I can write it like this. And that's a good way to think of the condition of integrabilities. I'm sorry because my F's look like T's, but they are F's, okay? Okay. They are related to the condition of integrability. When we do this thing, when we impose that this is equal to 0, indeed, what we are saying is that the Hamiltonian vector fields are tangent to the fibers, okay, defined by taking the set of first integrals. And that's a non-trivial thing, because once we have these first integrals, we can consider indeed this fibration, but we could also do something that it's a standard in foliation theory, which is consider the set of Hamiltonian vector fields as a distribution. And this distribution, indeed, if I do I need to teach more linear algebra courses first year to be quick. Okay, so this definition here, it's easy to prove. Well, that's an exercise. And that's an exercise, but that's also solved in the notes. You can look at the proof of this in the notes. Okay. Now wanting to. That the bracket, that the Poisson, that the Lie bracket of Hamiltonian vector fields is the Hamiltonian vector fields of the bracket. Therefore, this tells me that this is 0. This means that this distribution is formed by vector fields that they commute. So we have a funny relation between the commutation of first integrals and the commutation of vector fields. We have a lot of abelian things going on here. Indeed, this is not a surprise that we can do a fantastic thing, which is that in the case in which these vector fields are complete, this could happen if your manifold is compact, for instance, then there is an interesting thing going on, which is I can define an action in the neighborhood if I have a compact fiber. And that's a brilliant idea. I don't know who was the first to have this brilliant idea. It was not me, for sure. At least it was Doistermat. I learned this from Doistermat. I'm going to call this Doistermat trick. Which is, I consider a joint action. I can consider a group action, abelian, associated to this flow. Just by composing the time t maps time S1, I'm going to take the first one, first Hamiltonian, composed with time 1, time 2, second Hamiltonian, and I can apply this. And it turns out that this is a group action. Phi, and that's a brilliant thing, defines a group action. Then if you assume that your leaf is compact, because of the standard theorems of identification of the orbit space, and this is the orbit of your group, as I have checked, I have said it very quickly, that you have that the foliation given by this coincides with the vibration, and that's a kind of miracle that happens here. And therefore, this tells you that if you look at a compact leaf, this compact leaf has to be isomorphic to the group quotient by the isotropy group, and the group here is Rn. So this is telling you from the classification, what I'm doing now is a speedy version that you can find in the notes, okay? That this is telling you that that if you want L to be compact, okay, this Gx X has to be a lattice of Rn. Therefore, the leaf coincides with this quotient, and therefore, this proves in particular that the leaf has to be a torus. What I have done now is to prove for you what is called Liouville theorem. That tells you that the compact level sets of an integrable system are tori. There is a weak game here between vibrations and orbits of Hamiltonian vector fields of distribution. And it's quite clever game. It works because we are in the Lagrangian setup. So compact level of an integrable system are tori. Indeed, this is attribute, I mean, this is called Liouville theorem, but Liouville didn't prove this. Liouville proved that there exist invariant submanifolds. He didn't prove that they are tori. But you can prove that there are tori by using this Doistermat trick. This Doistermat trick is super powerful because you can go one step over. You can go. You can now consider the collection of isotropy groups and do something that is called uniformization. I'm going very quickly, sorry. Uniformization of isotropy groups. And this gives you an action of a torus on the neighborhood of the torus, of the Liouville torus. And this is fantastic. What I'm doing now, without wanting to do it, is to prove action angle coordinates. So I'm going to stop sharing and I'm going to share. Now, I don't know, I went over time. Can I take 5 more minutes? Catherine.
Minutes.
Yeah?
Yes,
Okay.
5 more minutes.
Okay, wonderful. So what I have done for you, well, here I put an example of an integrable system. Think of the coupling of 2 harmonic oscillators. You can think of this. And well, what I'm trying to convince you is that many examples come from physics. Pau will totally convince you about this. So here, if I take the coupling of 2 harmonic oscillators, the total energy, so kinetic plus potential energy, it gives you the equation of a sphere of dimension 3. Therefore, you can use the angular momentum as a new invariant. So what I want to say is that many of the first integrals come from physical intuition. Okay, this is an example. This could be an exercise in the list. What I have done for you without knowing it, indeed, is almost doing the proof of this Arnold-Liouville theorem that is essential and will be fundamental tomorrow to compute the cohomology of these objects. Tomorrow, this is going to be very important. So what I have almost done for you, well, I have proved that there exists this torus action, but this torus action is very wise. It takes Darboux coordinates that I know they exist, and if you prove that this torus defines a Hamiltonian action, then it drags these Darboux coordinates in a neighborhood of a leaf. So what does this for you is to give you a collection of action angle coordinates, okay? And well, the level sets of the coordinates correspond to Liouville tori. And what happens is that the Hamiltonian flow on each of the Liouville torus that I proved is a torus, because I identified with the orbit of an action, is linear. And then, so you have the situation in which you have this vibration. Then these action angle coordinates, why are they so special? Well, they are special because they are telling you that in a neighborhood of a torus, you have a trivial vibration. For us, this is fundamental to do the computations in shift cohomology tomorrow. Then there is the problem of global existence. This is another question, that it's related to the Chern class of the vibration given by the collection of first integrals that we call moment map. Indeed, do we have the right to call moment map the collection of first integrals? This theorem of Liouville-Miner-Arnold tell us that we are right, we can do this. Why? Because at the end of the day, the proof, well, here I was giving some ideas why we call Miner, because Miner was the first one to give the formulas of action coordinates, which have which look like this. Okay, you just take in a neighborhood of your torus. Okay, this is a Lagrangian torus on it's a Liouville torus, it's a Lagrangian torus. Therefore, in cohomology, it's 0. This means that in a neighborhood of a Lagrangian submanifold, your symplectic form is exact. Therefore, you can integrate the one form given by this exactness over the generators of the cohomology of the torus. And this gives you the formulas for the action coordinates. This formula is often attributed to Arnold, but Miner wrote it first, to tell you the complete truth. Miner wrote it related to some problem in celestial mechanics, but he was not so known because he was more known for belonging to the resistance during Nazi times. So, well, what I was doing for you before is the proof of this action angle coordinate. And what's magic is the relation between these groups in the proof. You really see how you use the power of group actions to prove your theorem. I was exactly in this point when I was on my tablet. I proved for you that when you have these uniformizations, Well, the neighborhoods look like the cotangent bundle of the torus, okay? And then you can prove that this action is symplectic. That's there is a hint how to do it. And again, because in a neighborhood of your Lagrangian torus, omega is exact, automatically, if you have a symplectic action, has to be Hamiltonian. Therefore, the clever proof of Oistermatt is take your Darboux coordinates, well, a bit special, because you want to check that not only Darboux coordinates, but that some of the coordinates are precisely your first integrals. Take your Darboux Theodoric coordinates and just drag them by using this Hamiltonian action. This is how the proofs go. Okay. Then just to finish, it would be fantastic if there were no singularities, right? But it will also be very boring. And indeed, if you have a compact manifold and you have an integrable system, the maximum principle is going to tell you that you have to have singularities. What do we call a singular point of an integrable system? Is a point in which you have, sorry, here there is, it's not a typo that I put, okay, that the rank of the differential of f is less than n. Here the rank is missing. I will correct this. And as in Moser's theory, we can define what is a non-degenerate singular point. This is the image of non-degenerate singular points that are so important in Morse theory. And indeed, we have a kind of, so we can consider an integrable system with this kind of non-degenerate singularities. And what we will need from the theory of local normal forms is this theorem that indeed it was proved in the neighborhood of a fixed point by Eliasson and in a neighborhood of an orbit by myself and Nguyen Thien Sung. And we proved that there exist symplectic normal forms for integrable systems with non-degenerate singularities. These normal forms are going to be fundamental to compute the sheaves that give us the definition of geometric quantization that we will see tomorrow. And then what is the local normal form? You have some functions that look like ellipses, some functions that look like hyperbolas, and some functions that come in pairs that account for these focused singularities. What's nice, and that's the first thing that you will do in half an hour, is to prove that these are cotangent models. Indeed, that you can see all these models as a cotangent lift. Indeed, also the theorem by Arnold Liouville, this theorem, you can interpret it as the cotangent lift of translations of the torus. If you take a torus and you consider translations of the torus, then you take the cotangent lift to the cotangent of Tn, okay? Then this theorem is telling you that any integrable system looks like a cotangent lift. And then in a neighborhood of a singularity, we also have such a result. And this is what Pau will prove this afternoon. So this afternoon, if you look at the list of problems, you have just 20 minutes to do these problems. You'll see that you have an harmonic oscillator, the simple pendulum, and the spherical pendulum. And Pau is going to precisely, this is going to be the starting point for the class this afternoon. Don't worry about these eight last slides. I knew I was going to stop here. The slide will go to the last to the last talk. So I stop here. Thank you.
Thank you so much, Eva. Are there any immediate questions? Here in the audience, I don't see any, but I'm sure there will be many later while we do the exercises.
Yeah.
There's a question back there. Just a second.
Okay.
Hello, Eva.
Hello.
Just this Oistermatt trick, I learned it under the name of Arnold's trick. So
Yes, I know.
Maybe historically.
Who did it first? That's a good question. Who did it first? The paper of Oistermatt is 80 something. I don't know. We should check, right? Well, this is in the book. This is in the. I mean, in the book of Arnold, you also find this proof. but I think that one of the Oystermatt is before.
From 78.
But I don't know. Let's say, yeah, well, maybe Arnold did it first. I don't know, but I understand that it's much more. In my opinion, it's much more clear in the Oystermatt. Arnold, Oystermatt, who cares? But what is clear is that the formula of action, the action formula, was first, but was before Arnold. It was 1936. You can find it in a paper in École Polytechnique. That I think, I don't know, Pau, if we added to the literature there. Otherwise, we should, okay? We always add it to our papers, like Miner was considered Miner. Yeah, I don't know, yeah. So it's essentially, yeah, it's true that the proof of Arnold in the book is the same as Oystermatt. Well, okay, yeah, I can call it Arnold Oystermatt trick. But I don't know, I like it a lot, the way it's explained in Oystermatt's paper. I think it's very clear. Because then you can also see, you can also try to extend these action coordinates and try to think of it more as fiber bundles. I don't know. I think it's more clear in Oystermatt. Does this solve your question? I don't see you. I don't see you. That's the problem, that I don't see the audience there. I just see Catherine.
Answer. Yes, he's happy with your answer.
Okay. Good.
So I think we're all ready for coffee. Of course, everyone who's here in Freiburg will be served coffee outside. And for everyone who's with us on Zoom, we will create breakout rooms. Actually, Mama will create breakout rooms and she will distribute you at random into those rooms. But of course, you can move about inside the breakout sessions. I suggest we take maybe 25 minutes of coffee break. So we'll start a little late, 5 minutes past 3 or so. But before we have our coffee, let's thank Eva again.
Thank you.